Hey everyone, welcome back. In this video, I wanted to take some time to talk about how to rearrange the order of integration when we're working with the tetrahedral type problems. I had gotten a couple of requests to look at this a little bit more closely, so we're going to do that by way of example, just kind of show a couple of different ways to rearrange this and really just kind of overview all the different ways to rearrange it, but we'll compute two specifically. Okay, so let's go ahead and jump in. This particular example, we're looking at rearranging the order of integration for this right here. It's a triple integral with the dx, dy, dz, and we have some function in here. We really don't care about what function is on the inside. We're really just focused on changing the order of integration here. And in this particular instance, we're asked to do it in two different ways. So before we start worrying about what the specifics of this are, I want to take a moment to talk about this. When we're saying two different ways, we're just talking about the different ways that we can order these right here. There are in reality six ways to rearrange this. We're already given one, so there are actually 5 ways that we can choose from. So I will make a note of that. There are 5 orders to choose from. And these are going to be dx, dz, dy, dy, dx, dz, dy, dz, dx, dz, dy, dx, and finally dz, dx, dy. And for our purposes, I mean, there's not really any rhyme or reason to this. This is just my decision as far as this problem is concerned. I'm going to decide to use, we're going to look at the dy, dx, dz rearrangement in this one, and we're going to look at the dz, dy, dx rearrangement, okay? But I mean, like, if you're ever given a general problem like this, you can choose any one of these rearrangements that you want, or a lot of times it's really popular to ask for all 5. So just so you're aware, these are the different rearrangements that it's referring to. So those are the options for order of integration. Okay. Great. So let's go ahead and start breaking down this problem. The first one we're going to look at is going to be this guy right here. And then the second one we're going to look at will be, not that one, this one. So before we get started worrying about what the bounds for these new orders of integration are going to be, is we're going to have to look at what kind of region we are considering. So let's go ahead. I'm going to rewrite this problem at the top of the new page. So we're doing the integral from 0 to 6, integral from 0 to 12 minus 2z over 3, and then the integral from 0 to 12 minus 3y minus 2z. And then this is of some function, f, x, y, z. And then this is in the order dx, dy, dz. And we can actually kind of tell, even without looking at the bounds here, what the order of integration has to be, because there's y and z present here, which means that this first one has to be x. The y has dropped out for the next one, but we still have z, so this next one has to be y. And then finally, z gets integrated last just by process of elimination. Because we want to make sure as we move from the inside out, we just have numbers here on the outside. But anyway, that being said, when we rearrange our order of integration, it has to be more than just saying, okay, we're just going to shuffle our bounds to match these guys over here. We actually have to mess with the variables that are inside of the bounds to make sure that everything gets integrated out. So to do that, we need to look at what our actual shape is that we're considering. And that's what the information we're going to get from this piece right here. This piece right here tells us, since this is the bound for x, that the region we're looking at is x less than or equal to 12 minus 3y minus 2z, okay? So this is our region. Okay, so, or maybe more generally, we can rearrange this to be x plus 3y plus 2z is less than or equal to 12, is a lot of times how you will see it stated. And this is going to be specifically in the first octant because we're looking at all of these being greater than or equal to 0. So if we want, we can kind of sketch this just so we see what we're dealing with. Although you don't absolutely have to be able to do these kinds of problems, but I do find it kind of helpful. So we'll call that 12. I know that y has to be less than or equal to 4. And that z has to be less than or equal to 6. Okay, so let's sketch this region here. It's going to look kind of like that. It's a tetrahedron like so. Okay, so there's our region. We want everything that's kind of on the left side, underneath, and toward us of this plane that's right here. So this sloped surface is actually this exact plane. The less than or equal to 12 is what tells us we want what's underneath. And specifically, this is in the first octant. Octants does not have an extra C in it. Okay, so now we are ready to start rearranging to get our integral. So the first one, we're doing a triple integral, f, x, y, z, and we said that our new order of integration was going to be dy, dx, dz. Okay, so to be able to do this, step one is we solve for inside variable, which in this case, that's our first one for integration. That's going to be y. And when I say solve for inside variable, we're looking at this equation right here. I'm going to solve for y. And I get that y is less than or equal to 12 minus 2z minus x divided by 3. And I already know that since I'm in my first octant, y is greater than or equal to 0. Okay? And in fact, I can fill in the zeros on all the other ones too. So anyway, but this immediately gives me my upper bound on y. 12 minus 2z minus x divided by 3. Second step, and this is going to be kind of the pattern that will follow for the next one as well. What you do is you set the completed variable, and by that I mean the one that you've already dealt with, I guess, equal to 0, and then solve for the middle variable, which in this case is x. So we look at this guy right here, set y equal to 0, and we're going to solve for x. And I'm going to get that x is less than or equal to 12 minus 2z. And again, since we're in the first octant, x has to be greater than or equal to 0. So that gives me my bounds for x. And then finally, we set the completed variables, both of them equal to 0. Solve for outer variable, which in this case is z. So here, I'm going to set x and y equal to 0, and I'm going to get z has to be less than or equal to 6, greater than or equal to 0. And this makes sense because this is the highest value that z can achieve based off of this piece right here. So 0, 2, 6. And that is one possible rearrangement for this integral. That's pretty much all there is to it. You just walk through this process right here and you get those bounds. So we're going to do this one more time. And this time what we are going to go for is, I think we had said dz, dy, dx. So we have triple integral of some function f, x, y, z, which, by the way, since we're not changing coordinate systems, we're just changing bounds, not coordinate systems. Nothing about the region is changing the way it's expressed or anything like that. This piece stays the same. And now we're just changing order of integration, and I get dz, dy, dx. So step one, solve for inside variable. This is z. So again, this is going back to what our expression for our region was, which is this guy right here. And I'm going to get that z has to be less than or equal to 12 minus 3y minus x, and then all divided by 2. And then again, because we're in our first octant, we know that z is greater than or equal to 0, which, like I said earlier, is something that we can just go ahead and apply to all three variables because we know that all three of them have to be greater than or equal to 0. Anyway, my upper bound for this is 12 minus 3y minus x, and then this is all divided by 2. Okay. Now we solve for our middle variable. We're working with y now, so we set the completed variable equal to 0. So that's going to be z is equal to 0, solve for middle variable. And in this case, that's y. So we set z equal to 0 in this expression right here. We're just looking at solving for y, and we're going to get y is equal less than or equal to 12 minus x, and then that's all divided by 3. So that's my upper bound for y. Just like so. And then finally, same idea when we're working with the third one. Set completed variables equal to 0. Solve for last variable, which in this case is just x. So we're going to get that x has to be less than or equal to 12, looking at this guy right here, which again, that kind of makes sense because I guess x, y, z. Along here, that's the largest value that x could possibly achieve. And that's pretty much all there is to it. One big question that I typically get is why can't we just go ahead and put constants in for each of my x, y, and z? So why can't I say that, for example, if we look at this one, why can't I just say that z goes from 0 to 6, y goes from 0 to 4, and x goes from 0 to 12, and y goes from 0 to 4? And the reason for that is that if you keep those constant bounds, what you actually wind up with is going to be the full rectangle here instead of this nice sloping thing that you've got going on. And these variable bounds here actually account for the slope that occurs here. That's your slope that's, kind of three-dimensional, okay? And then this is a slope that's just a line, and that's where this guy comes in right here. So this accounts for this slope, and this accounts for kind of like the roof type slope that you've got there. And then finally, after you've accounted for those two slopes, then you can just say, okay, yeah, my last variable can be constant along there. So, but yeah, anyway, that's kind of the process for working with these kinds of problems. And it is a little bit confusing at first, but there is a little bit of some, I don't know, just kind of some mechanics you can follow with it. So yeah, I'll see you guys next time.